Okay. Hi everyone. We're a mechanical engineering capstone group, and our problem is orbital safety is outpacing small satellites.
The small satellite industry is expanding rapidly, making space more accessible for university teams, startups, and commercial operators. But with this growth comes an increasing amount of congestion in orbit. This problem is not just the number of active satellites, it's also the amount of space debris. The ESA reported that there is 1.2 million pieces of space debris between 1 and 10 centimeters in orbit right now.
Many of these smaller debris are often difficult to track and hard to avoid. When collisions occur, they generate even more debris, leading to a cascading problem that increases the risk of future collisions. At nearly 28,000 kilometers per hour, even millimeter-sized debris can disable subsystems, damage spacecraft, and catastrophically fragment an entire satellite. For operators, this means service disruptions, lost revenue, and higher mission risk.
Regulations are becoming stricter, and orbital safety is becoming more urgent. Disposal expectations have shifted from a 25-year guideline to a very strict 5-year deorbiting requirement for US and Canada satellites. As a result, small satellites increasingly need practical maneuvering capabilities and deorbiting capabilities to remain compliant.
For small satellite teams, orbital safety is no longer just a nice to have, it has become a requirement. From a company perspective, this creates pressure across the business. Legally, teams are required to prove a credible disposal plan before launch. From an engineering perspective, it is difficult for many low-cost CubeSat operators to add propulsion due to increasing cost, sacrificing payload capacity, and additional integration complexity.
So the problem is not just engineering, it's operations, finance, sustainability, and customer trust. As safety expectations rise, CubeSat teams are simply not able to afford, integrate, or power existing propulsion solutions. Our problem is simple. Without a practical way to deorbit and collision avoid, these small satellites are entering a very congested market without any way to meet their expectations.
The problem affects the entire satellite ecosystem, such as CubeSat operators, universities, startups, manufacturers, launch providers, and regulators. The numbers show why this matters. The global small satellite market is expected to grow from 5.23 billion to 11.28 billion, while in North America, the market is expected to grow from 2.37 billion to 5.12 billion. Yet, despite this rapid growth, many operators still lack a practical and affordable way to meet the developing orbital safety guidelines. The market is growing faster than the industry's capability to support it.
This problem has been building for decades. In 1957, Sputnik became the first artificial object in orbit. In 1978, Kessler introduced the idea that as these objects accumulate, there will be an increasingly cascading debris problem due to collisions. As space became cheaper, CubeSat teams increased the amount of small satellite missions in orbit. Major debris events such as the 2000 Chinese anti-satellite test and the Iridium Cosmos collision showed that debris in orbit is no longer just a theoretical concern. It is an operational challenge.
As orbital safety requirements continue to increase, operators need more than just a propulsion system that works. They need one that is affordable, easy to integrate, and launch safe. This is where the propulsion gap appears. Existing technologies only solve part of the problem, while most of them force a trade-off. As shown here, chemical systems provide rapid thrust, but increase cost and complexity, while electric propulsion is efficient but requires high power demands and long maneuver times. No existing solution satisfies all the practical requirements of small satellite operators.
So there are already capable propulsion systems, but the problem is, for the average 10-kilogram CubeSat, these propulsion systems take up too much of the scope. They take up to 25% of the mass, 33% of the volume, and 70% of the operational budget. While this might be okay for large satellite companies, for small satellite companies, that means a decrease in payload, increasing integration complexity, and increasing power requirements. The gap exists that propulsion systems are being able to be used to meet compliance expectations, but they simply aren't suited for small satellites and use up too much of their limited resources. The ideal solution would be able to fit the mass, volume, and integration criteria while still being reliable and safe.
To summarize, the problem is that orbital safety expectations are rising faster than small satellite capability. That is why we believe this is a problem worth solving now.
Time's up.